The next is a small signal dynamic performance. Later on, we will use the CS stage or other stages inside feedback amplifiers as a part of a controller of a feedback amplifier. And then we need to know what is a dynamic behavior, what poles are introduced in the loop by such stages. So we really need to know the behavior. And if the behavior is very complex, we want to know, can we do something about that? Can we use it under certain conditions that we can guarantee a more orthogonal design and even a minimum number of stages for a maximum bandwidth? Such questions that we are going to answer later need this study that we are going to do now. So for those who do not know, we are going to about the transmission one matrix. Please go to the homologation program, because there's a lot of stuff about the transmission one matrix on this in this program, and you can find exactly the definitions of everything required here. And for the others who already did, they here is to remember, and there's an error in the sheet again, and this is the error because it should be ABCD and not ABCC. This is to keep you awake. I will change it in ABCD in the on the web presentation. So this is the definition. It is a so-called anti-causal notation, because we write the input quantities as a function of the output quantities. Of course, this is not how it works. So if we are going to measure them, we apply something to the input and we measure the response at the output, and then we take the inverse to get the parameter. And this is what we will do for the biased CS stage. So consider this block now as the biased CS stage, and we are going to determine A, B, C, D, and the input and the output impedance. So let's start with A. A require is the VI as a function of VO, so we're going to measure it the other way around. We apply an input voltage and we measure the open circuit output voltage. And the first question I have, and I see Chris is gone, but we need him for the poll. Oh, there it is already. How many poles does this circuit have? Well, I think this still needs some attention. So let's go back to the definition. The number of poles of a circuit is a sum of the number of free independent capacitor voltages and free inductor currents. So we have no inductor, so that makes it simple. We have 3 capacitors, so it will never be more than 3. So 4, I don't understand. 3% 4, probably 1. No, there are 3 capacitors, so it cannot be more than 3. But it's also not 3, because the number of independent capacitor voltages is the number of capacitors minus the number of loops of capacitors, or loops of capacitors and voltage sources. And with loops in this case, I mean independent loops. And how did we find independent loops? We found independent loops by breaking loops until there's no loop left. Okay, so let's do it. I have a loop here of a capacitor and a voltage source. I have a loop here of 3 capacitors, and I have a loop here of 2 capacitors and a voltage source. How many of those loops are independent? Now, then we could do another color. If I break this loop, so I take just away 1 capacitor, I still have this loop left. And if I break this one, then there's no loop left. So there's 1 independent capacitor voltage, so there's only 1 pole. And of course, you could have done the same by sorry, I must do the other knob, by calculating it. But that's no fun. It's much more fun to estimate it before, because if you every time you have to do this calculation, you are not going to like analog electronics anymore. So that's why we would like to teach you to do these fast estimations. So basically we have only one pole, and the pole is here, is written here. It's like this capacitor in parallel CGD in parallel with CGS over RO. You can see this is just a short to ground, and then you have two capacitors in parallel with RO, and that is this SRO CGD plus CDS. And here you see the right half plane zero that we talked about. And you see here there is a transfer from VI to VO through CGD, but there's also a transfer because of VGS and GM, the controlled source. And that means that you can see that if the transfer of GM VGS, if it is exactly the same as the current through this one, then they both cancel. There's no current left for the output, zero left. This one eats the other current, and VO is zero, and that is the frequency of this zero. Let's go to the other one. Let's go to parameter B. Parameter B is we drive it with a voltage and we measure the short circuit current. And measuring the short circuit current is done in the short circuit, which is a voltage source with zero voltage. And here again, we have the question, how many poles? And now you know the rules, and now I hope many answers will be okay. Now I see again an answer like 4, but I don't see 4 capacitors, so this must be a mistake. So there can never be 4 states if there are no 4 reactive elements in the circuit. I also see 3, but we already know now what is the answer. The answer is the number of independent capacitor voltages. We have 2 voltage sources. CGS is connected across a VI, which means if you put charge on CGS, it will immediately cause instantaneous a huge current in VI, and the voltage will remain the same. So it's not a free voltage because the voltage is set by VI and it cannot be free. If you put a voltage on CDS, it's the same story. Any charge you put on CGS will immediately result in a current through VO, because the voltage across CDS is VO, and it's zero in this case. It is not a free voltage. And now look at CGD. The voltage across CGD is also set by the 2 voltage sources. It's VI minus VO. So it is not a free voltage. So in this case, we have 0 poles. And there's only 20% correct here. We have given a lecture about poles and zeros last year. It's in the homologation program. If you really want us to do it again, of course we can organize that because this is an important topic to estimate poles and zeros from networks. So, and the first step is how many poles are there and how many zeros are there. And now we do only poles. So here we don't have any poles. We only have a zero. Because we have a differentiation from the voltage VI to the current IO. And that's what you see here. And it's a zero in the right half plane. Exactly the same. All the transfers have this zero in the right half plane. So no poles. Only 20% correct. The next one, I think we keep on going with these questions. Chris, don't you think so?
Yep.
Let's do this. We have current in and voltage out. So here's the question again. How many poles?
Well, I'll stop this polling now. These are the results.
Okay, well, we have kind of Gaussian distribution with a peak at 2. Some people think there is no, and there still is an answer like 4, but I still have 3 capacitors. So I don't know where this answer 4 is coming from because it's appearing all the time. But we still have 3 capacitors. And if we have 3 reactive elements, we can only have 3 poles. But the number of loops, well, let's see here. I have 1 loop of capacitors here. I can break the loop by taking one of the capacitors out of it, and then there's no loop left. And you see, then we have here a pole in the origin because this one is discharging over an infinite impedance, and this one is discharging over RO. So we have a one at CDS RO if the gate drain capacitance go to 0. This you would also like to see in the expression later, of course. The expression is quite complicated, but it fits. So again, so GMRO is a DC gain. We put the current divided by SCS. You see, there's 1 pole in the origin. And I know we're a little bit over time, so I just finished this one, and the D we do in the next section. Yeah, Chris?
Yeah.
So we have 1 integrator pole here, and we recognize, I hope you recognize here, what you know as probably know as the Miller effect. 1 plus the voltage gain times CGD. This is a huge input capacitance. And then we have here a second pole. I wrote it in this way, so we have SRC, and you can estimate this capacitor that is here, how large it is, and see where the second pole is. And the second pole, let's say if CGD would be 0, then you see the second pole, CGD, would be CDS RO. That is, you can fill in the equation and you will find that that will be true. But if it is not 0, we have something interesting. Then we have a pole at 0, and we have a pole, of course, at this frequency, and 1 over RC omega. And the nice thing is here that if CGD, oh, this is also, this should be CGD smaller than CGS, and this should be CDS smaller than CGD. I will correct it in the slides. So if that is the case, then the numerator simplifies very much. You only have CGS there, and then you see that if we have only CDS there and it doesn't depend, then this one, if the Miller effect is really dominant, then this one depends in the numerator, which means if the CGD gets larger, this one goes to a higher frequency. That is something we can easily see later on from an equivalent impedance circuit. And this is called pole splitting, because if CGD gets larger, this pole, well, it's already in the origin, but that's the gain drops. But this pole goes to a higher frequency. And you can calculate that the product of the poles remains the same, but the sum increases. And this is called pole splitting. So the Miller effect is not only making let's say, the bandwidth smaller, but also bringing the non-dominant pole to a higher frequency.